All right, so firstly, I want to talk about our first exam arrangement. This morning, I sent out the emails reminding you to look at announcement I posted in Blackboard. Did you guys read the announcement? Hi, Angie. Okay, very good. To answer your question, the time window for you to take the exam one is from February 19 to 28. That is many days, right? 1, 2, 3, 4, like over 10 days. You may take the exam anytime when the TCC testing center is open. I do not have a favored time for you. You take the exam at your convenient time. Did I answer your question? Okay, very good. Our exam is when? Our exam is when? You can take it anytime between February 19 to February 28th. Anytime in that time window. I'm pretty flexible. And your responsibility to figure out the hours and locations of the testing centers. All right. I think they have some changes this semester. On Saturdays, not all the testing centers open. In the past, Southeast is the only campus have the testing center open. And maybe something is different. So I would like you to figure that out. Call them, So we can take it on the 28th until the end of the day. Until the end of the day. Yeah, let me see what what day of 28th. 28th is Friday. Yeah, you can take it on Friday. I wouldn't say the end of the day. The end of the day, the midnight, probably the testing center not open, right? And also maybe the hours on Friday is different. So I would like you to figure that out. In our website, on our website, search testing center. You will see their hours, their locations. Okay, very good. Do you guys have any other questions? You received the emails from testing center as well, right? The emails tells you your instructor has arranged the exam with the testing center. And let me know, at least one of you, I have not received that email. Okay, let me show you what I'm talking about. You're supposed to look at your email box. You're supposed to not this one. This one. Not from me, from Tulsa Community College. You see that? This one is this one. Hello, your instructor Jianbo Guo has requested that an exam be made available for you for the following class. And those are two sections, 1 p.m. class, 903, 904. Can you look at your email box and let me know at least one of you has received this confirmation? You haven't? Really? Jennifer hasn't yet? Did you look at it? Did you look at your mailbox, your email box? So, yes, you have looked at it, but the email isn't there. Okay, Angie's seen it. If Angie has seen it, that means maybe check your spam box. You're supposed to receive an email like this, all right? Time limit 80 minutes. The test is available from February 19th to February 28th. You must take your test by the end of the month. Plan to arrive in time to complete your exam. If they close at 5, just for example, then please don't go there like 4:30. You're gonna give yourself enough time, sufficient time to prepare and complete. Please go to any testing center at Tulsa Community College, take your exam. For hours, contact numbers, and the location, please view. Yeah, if you click the link, you will see the page with the hours and the locations. All right, please look for this email in your box. Do you guys have any other questions about the exam? Okay, then we can start our lecture for today. I have looked in the junk box and it's also, oh, I don't know. Yes, Cindy saw it. Maybe Ashlyn email me about that and I will forward your email to testing center. Let them know some of the students have don't have the emails. You're welcome. Okay, let me get my notes. You guys remember arguments, right? The last two sections of this chapter is about arguments. And we focus on testing the validity of an argument. Last class, section 3.7, we learned a tool. The tool is the truth table. We use the truth table to test the validity of an argument. So that's what we learned in section 3.7. Today, we scheduled to cover section 3.8. We're going to learn another tool that can test the validity of an argument. And then the tool is the Euler diagram. Talk about Euler. I want us to look at a very brief introduction of this mathematician. 3.8 here. Just take a couple minutes to show our respect. Leonhard, I actually don't know how to pronounce his first name. Euler, Germany, 1707 to 1783, whose last name rhymes with boiler, not ruler. So I think pronounce his name correctly shows respect, right? Is the most prolific mathematician in history. Is not even one of the most, it is the most. Euler published an average of 800 pages of new mathematics per year over a career that spanned decades. Euler invented an elegant way to determine the validity of arguments whose premises contain the words all, some, and no or none. Okay. A statement that contains those words are called what? It's called a quantified statement, right? Those are quantifiers, if you remember from previous section. All, some, no, none, they are quantifiers. A statement containing those words are quantified statements. Do you guys remember we have 4 types of quantified statements? Let me give the 4 quantified statements for you. The first one, OARB. This is a Euler diagram, right? Euler diagram does not have the boxes. The diagrams with boxes, those are Venn diagram. Here, Euler diagram. This is the Euler diagram that represent this quantified statement. All A are B. The set of A is completely inside the set of B. It gives a subset relationship. The second type of quantified statement, no A are B. A, B are disjoint. They have no overlap apart. They have no common elements. There's no A or B. And the third type, we have a dot here, all right? Very important. Some A, my bad, sorry. I meant the third type. Some A are B. Some A are B. The first type is some A are not B. Some A are not B. All A are B gives a subset relationship. No A or B gives a disjoint relationship. Some A are B, some A are not B. Those two quantified statements give a overlapping relationship. But some A or B stress at least one element in the overlapping region of AB. Some A are not B stress there at least one element that is in A but not in B. Okay, so those are the four quantified statements. I don't know if you also remember those two. They are negation of each other, and those two are negation of each other. The negation of all A or B is some A are not B. The negation of no A or B is some A are B. All right, that's from previous sections. We needed it in this section. We need this. And we talk about two tools, right? Last time we learned truth table. This time we're gonna learn using Euler diagram to test the validity of an argument. Euler diagram. And the process of the application of Euler diagram in determining the validity of an argument can be summarized in 3 steps. Let's look at the 3 steps, right? Euler diagrams and arguments. First step, make an Euler diagram for the first premise. Do you guys remember what is the premise? An argument, what is the premise? Okay, very good. Just quickly review. An argument look like this, right? Premise 1, premise 2. An argument could have one premise only, or have 3 or more. But the arguments we see in this section, most of them have 2 premises. So first premise in this line, and then follow the second premise under it, and then we have a horizontal bar separated the premises and the conclusion. This means therefore conclusion. So the method of using Euler diagram to determine the validity of an argument is to describe or represent the first premise using Euler diagram, and then make another Euler diagram to represent the second premise, and then draw the diagram on top of the one for the first. Not literally on top of. It's basically make a Euler diagram combining both two premises. Step 3. The argument is valid if and only if every possible diagram illustrates the conclusion of the argument. If there is even one possible diagram that contradicts the conclusion, this indicates that the conclusion is not true in every case, so the argument is invalid. Let me summarize in my own words. My understanding here, to apply the method, to apply Euler diagram to test the validity, our goal after creating those diagrams, our goal is to try very hard to show the argument is not valid, is invalid. If we try very hard but fail to show the argument is invalid, that means what? That means the argument is valid. You see that? If you are going to be a lawyer, or if you are familiar with the legal system, kind of similar with that, right? If you some system assume the what is the person? Assume the person is innocent, right? And then you try very hard. Assume he's innocent, and then you try very hard to prove he's guilty. And some system assume the person is guilty and then try harder to, very similar. So here we assume we try very hard to show it's not valid. If we fail to show it's invalid, then it is valid. I think the best way to do that, to understand the method, is to use it. Okay, we can understand this paragraph as well. The goal of this procedure is to produce, if possible, a diagram that does not illustrate the argument's conclusion. You try to figure out a case to show the argument is invalid. The method of Euler diagrams boiled down to determining whether such a diagram is possible. If it is possible, this serves as a counterexample to the argument's conclusion. An argument is invalid. By contrast, if no such counterexample exists, then the argument is valid. Basically the same thing with what I just said, right? Yeah, try to understand, and then maybe you can summarize it in your own word. Let me give you a little bit of time, all right? Yeah, how does this method work? The idea. Okay, read it, and then we'll start to look at the examples. Basically, we assume the argument is invalid. So try very hard. It is guilty. Try very hard to find something to prove, to find evidence to prove it's invalid. But if you fail to find the evidence to show it's invalid, then you have to admit it's valid, right? Yeah, similar with the example I gave you. All right, ready for the examples? Example 1. Have to enable editing, then I can write something here. Okay. Use Euler diagrams to determine whether each argument is valid or invalid. The first one, as you can see, there's a bar, right? Above the bar, we have two sentences. Those are the two premises. The first premise says, all US voters must register. Second premise says, all people who register must be US citizens. Therefore, below the bar, we have the conclusion. All US voters are US citizens. Okay, let me show you how to apply the Euler diagram to determine the validity of this argument. First step, read the first premise and trying to use a Euler diagram to represent that premise. The premise here, all US voters must register. premise 1. All US voters must register is a quantified statement. It basically says all voters are registers, right? Basically says that, right? All US voters must register. We know it's about United States, so we don't have to mention a country. All voters are registers, right? Do you agree that means the same thing? All voters are registers. So that's the first type of Euler quantified statement. Yeah. So we can use this diagram to represent the first premise. All voters are registers, right? Yeah, all voters are registers. All voters are registers. That's the first premise. Second premise. All people who register must be US citizens. Okay, I can rewrite that premise as all registers are citizens. Means the same thing, right? All registers are citizens. That means the second premise is also the first type, the subset relationship, the first type Euler diagram, right? Okay, since we already have the circle registers, the bigger circle here representing US registers, right? The people who registered. So we're gonna use that. All registers are citizens, so we can draw a bigger circle. That the circle registers can fall inside the bigger circle, and the bigger circle would be all citizens. And this diagram would have both premise 1 and premise 2, right? Voters are registers. All voters are registers. All registers are citizens. So that's the Euler diagram. Are we able to show, all US voters are citizens, to show this conclusion is wrong? It's not going to happen. Okay. Can we show all US voters are US citizens? No. Yeah, because you're right. We cannot show that conclusion will not happen. Very obvious that conclusion will always happen. Because the voters is inside registers. The registers is inside the circle of citizens. So the circle of voters is inside the circle of citizens. I can use a different color. So all voters are citizens, right? If there's no another way, there's no another possible diagram or different diagram would say the opposite of the conclusion. If you're interested, let's go back. Sorry. If you're interested, let's go back. What's the negation of all ARB? The negation of all ARB is the two circles overlapping, right? And then we have an element in A but not in B. But from our diagram, the two red circles, they are not overlapping. There definitely is a subset relationship. All voters are citizens. This one is pretty simple, by the way. So it's valid or invalid. From the diagram, we can show the conclusion always happen. Always happen. Do you see that? Please let me know. Okay, very good. I want to make sure everybody's with me. And we don't have much to cover. No, not don't have much to cover. Actually, yeah, really don't have much to cover. section 3.8. So we will finish this section and then go ahead to start the review. All right. Review has 45 questions, so we really want to have more time on that. But we need to learn this section as well. That's the first example. Second example. First premise. Premise 1. This one. It says all baseball players are athletes. Yeah, we can actually read the whole thing, whole argument. All baseball players are athletes, and premise 2 says all ballet dancers are athletes, and conclusion, therefore no baseball players are ballet dancers. So after I read this argument, I think I need 3 circles for the diagram. 1 circle represents all the baseball players. 1 circle represents all the athletes. 1 circle represents all the ballet dancers, right? We need 3 circles. Okay, let's see what's the first premise. All baseball players are athletes. So we have this relationship, right? Yeah, baseball players. Baseball players. Okay, all baseball players are athletes, right? Yeah, so that's the first premise. The circle of baseball players completely fall inside the circle of athletes. Premise 2. Premise 2 is also this subset relationship. It says all ballet dancers are athletes. All ballet dancers are athletes, right? Can we disprove this conclusion? Can we find a case to show no baseball players are best dancers is wrong? Huh, guys? What I show, my diagram right now, baseball players, this circle baseball players and the circle ballet dancers, they are disjoint, right? Yeah, if 2 circles are disjoint, so we wanna prove the conclusion. I'm sorry, the conclusion actually is wanna show baseball, the circle of baseball players and the circle of ballet dancers do not overlap, right? That's the conclusion the argument wanna show. Yeah, that's the conclusion the argument wanna draw. We wanna find something to show that is incorrect. We wanna find something to show that is incorrect. Let me see if I can just do this part. Okay, this seems together. Right now my graph is supporting the conclusion, right? But I can, draw another one. Ballet dancer. This one would serve as a counterexample, right? You see that? Baseball players, ballet dancers, they could overlap. They don't have to disjoint. Yeah, I could draw the 2 separate, then that's disjoint, but I could also draw them to overlapping. You see that? Yeah, there are some ballet baseball players, they are ballet dancers, right? So what does this mean? I found a diagram. I found a case in which baseball players and ballet dancers are not disjoint. It's different, right? It's go against that conclusion. So valid or invalid, everybody? Is this argument valid or invalid? Take your time. You're right. You're right, Charlie. You're right, Ashlyn. Invalid. Okay? I found this case. Look at the two circles, baseball player circle and the ballet dancer circle. They overlap. It's different from what the conclusion claims. The conclusion claims they are always disjoint. Not always. This diagram is the example that can show is wrong, right? So it's invalid. Do you guys see it, everybody? Do you guys see it? Perfect. Yeah, I want to make sure everybody sees it. All right, if you don't respond, perfect. Thank you, Jennifer. Continue. This one, premise 1, premise 2, conclusion. All right, premise 1 says all mathematicians are logical. Premise 2 says no poets are logical. Conclusion says no poets are mathematicians. Well, after I read this argument, I think I need how many circles, guys? Mathematicians, 1 circle, right? Poets, 1 circle. How do you represent people are logical? Logical people, right? Do you agree we need 3 circles? Exactly, perfect. Awesome, very good. All right. So all mathematicians are logical people, okay? Mathematicians. Okay. All mathematicians are people or logical people or people who are logical. How about that? People who are logical. Okay, all mathematicians are people who are logical. Logical. So that's the first premise. Second premise, no poets are logical. No A or B. That is a disjoint relationship, right? Yeah, which 2 circles gonna be disjoint? We're gonna show disjoint. Poets and people who are logical. Okay, so this circle can represent poets. No poets are logical. So the circle of poets and the circle of people who are logical should be disjoint, right? Do you see what happened? Yeah, after we draw the diagram to represent the 2 premises, can we draw the conclusion? Says no poets are mathematicians. So the conclusion wanna say the circle of poets and the circle of mathematicians are disjoint. That's the conclusion I'm trying to say. The conclusion wanted to say the circle of poets and the circle of mathematicians are disjoint. Do we always have that? Or is it possible they do not disjoint, they overlap? Okay, look at it here. This is the circle of mathematicians. The blue one is the circle of poets. Is it possible for them to overlap? Is it possible for them to overlap? Not possible. You're right. You're right. Thank you, Jeb. Thank you, Cindy, Ashlyn, and Jennifer. Exactly. Not possible, right? If the purple circle and the blue circle want to overlap, then the blue circle has to overlap with people who are logical, and that is not true. That is premise 2 says they are disjoint, right? If the circle of poles is disjoint with the bigger circle, as a part of the bigger circle, Paul is gonna disjoin with mathematician. So this is a valid. I hope you see it, guys. This is pretty straightforward. This is pretty straightforward. So this is valid, all right? Next, I'm gonna give you a couple minutes. Try on your own first. Yeah, try on your own first. Figure out how many circles do we have. All actors are artists. We need the circles, right? 2 circles. 1 circle for actors. The second problem says Michelle Rodriguez is an actor. Just wanna this is one person. You're gonna use 1 dot. You don't need a circle for that, okay? You do not need a circle for Michelle. Later, when we go to review, we'll see some problems regarding Euler diagram. Okay. I assume you have your diagram. Let's see if you have the same with mine, okay? First premise, all actors are artists, right? All actors are artists. So the circle of actors fall completely inside the circle of artists. That's the first premise. Second premise, Michelle Rodriguez is an actor. How about we let this big red point to represent Michelle? Okay, yeah, she's an actor, so this dot that represent her gonna fall inside the circle of actors, right? Can we draw the conclusion that Michelle is an artist? Yeah, I think it's really obvious. Or if we want to show, if we want to find something not support this one, then we have to show Michelle, this dot represent Michelle, is outside the circle of artists. It's not possible, right? It's not possible. Yeah, so this is valid. Do you see it? It is valid. If the dot fall in a small circle, it's not possible for the dot to fall outside the bigger circle, right? Yeah, if the point is in a small circle, then the point is in a bigger circle because the small circle is a subset of the bigger circle. So that give us, always would lead to the conclusion Michelle is an artist. And actually, this is not just valid, is a sound. Remember what is a soundness? For an argument to be sound, the argument needs to be valid at the first place. On top of that, all the premises need to be true. All actors are artists. I think it's true. I think, I think I can see that as true. All actors are artists. And Michelle is an actor. I believe that's true. I don't know who she is. I think maybe she's true. He's an actor. So she is an artist, right? This argument kind of like using deductive reasoning. Any questions, guys? Yeah, do you have a feeling about this type of problem? Is your graph pretty similar with mine? Okay, very good. Thank you. And let's continue. Some houses. This one is a little bit challenging, okay? Let's read it. Premise 1, premise 2, therefore conclusion. All right. Premise 1, some houses have 2 stories. Premise 2, some houses have air conditioning. Conclusion, therefore, some houses with air conditioning have 2 stories. Okay, think about how many circles do we need? How many circles do we need? We need a circle represent houses, right? Okay, we need a, how many circles? We need 3 circles. Okay, let me show you. This is how I process this problem. Let me know if you have different opinion. Some houses, okay, this circle represents houses, right? Some houses have 2 stories. I can use this circle represent things that have 2 stories, right? Yeah. Not just the houses have to have stories. I think some buses have 2 stories. Can you say some furnitures have 2 stories, right? Yeah, a lot of things could have 2 stories, right? So the first premise says some houses have 2 stories. That means those 2 circles overlap. There's a dot here, right? That's the first premise. Second premise, some houses have air conditioning. I use the same idea. I'm going to draw another circle. This circle represents things with AC. Not just the houses have AC, right? I mean, not just the houses could have AC. Vehicles, cars could have AC. What else could have AC? A boat. Boat kind of like a type of vehicle, right? In a sense. Well, anyway, a lot of things could have AC, right, installed. So this part, houses and things with AC overlap, represent the second premise. Some houses have air conditioning, right? All right. Now let's look at our conclusion. Let's look at our conclusion. What our conclusion want to say? Yeah, the conclusion of the argument want to say. The conclusion of the argument says some houses with air conditioning have 2 stories. Okay. Do you agree this region represents houses with air conditioning? This purple region represents houses with air conditioning, right? Yes, some of them have 2 stories. The conclusion want to show those 2 shaded regions overlap. Yeah? Do you agree, guys? The conclusion want to say those 2 regions I shaded in purple, they overlap. But my graph shows they don't overlap, right? Then my graph could serve as a counterexample to show the conclusion is not always true. It's not always true. So this is invalid. This is my conclusion. This is my test. Okay. What do you think? Do you agree my result? I don't see the region that shows the conclusion. Does that make it invalid? Yeah. Okay. In the conclusion, basically, we have 3 circles. You agree, right, guys? We have 3 circles here. You agree? The circle of houses, the circle of things with 2 stories, the circle of things with AC, right? We have 3 circles. The conclusion wanted to show the 3 circles all overlap. Like there is a region here shared by all 3 circles. That's what the conclusion want to say. The conclusion want to say some houses with AC also have two stories. So basically, the conclusion want to show the three circles all overlap. There's a region belong to all three circles. But my diagram here says the opposite. That's why we conclude it's invalid. What do you think? Do you agree my result? Sometimes we try not to. You're welcome. That makes, yeah, okay. Yeah, sometimes we try not to make sense of the sentences. As we know, we are only testing the validity. We don't care the soundness, right? And let's see. Some houses have 2 stories. Oh, that's true. Some houses have air conditioning. That's true. But logically, the two premises do not directly lead to the result, the conclusion. Since it's not valid, we don't consider soundness, because in order to be sound, the argument has to be valid first. Yeah, it means some houses with air conditioning. Okay. Yeah, logically, I don't think, yeah, obviously my drawing, my diagram shows the opposite, right? Shows the opposite. Okay, that's everything about section 3.8. You guys ready for review, exam review? Let's get started. Very, very important. We only have 3 exams. The first exam is very important. If you do well, you will have the confidence, your confidence to continue and feel good the rest of the semester, right? But if you do bad in the first exam, you will feel miserable the rest of the semester. My point is to try to get yourself ready. Okay, I want to show you this. Do you see the green flag? If you do not have the green flag disappear, do not go to testing center to take your exam. Only when the green flag disappears, you have the access to the exam. How to make the green flag disappear? You're gonna practice your review and pass the review with at least 75%. Even I stress this over and over again every semester, there are always students are not ready. I know you have a life, you have so many things to do, but it is okay. You have to pass the review in order to have the access to the exam. Let's go to the review. We have 54 questions. The actual exam might have only 30. Yeah, so this is more than what do we have on the exams. Let's look at the first question. Use the Venn diagram. Venn diagram is different from Euler diagram. Venn diagram has the box, right? Box represents the universal set. Represent the set A. Yeah. Do you remember what is this? Is this A or B? Or is this A and B? This is from chapter 2. A and B, exactly. Intersection, perfect. Yeah, thank you, Charlie. Intersection, exactly, awesome. It is intersection. Intersection means and. Then the elements in the intersection of AB include the common elements of AB, right? Use a comma to separate. Okay, the common region, AB common region has 2 elements, 9 and 12. 9, 12. And when you do the review, you will not have immediate feedback. You would have to finish all the 54 questions and then see which question you get it wrong, which question you get it right. But I'm sure this is, I guarantee this is correct, right? Number 2, determine whether the statement true or false. The statement says 12 is not in the set. The set has a 1, 2, 3, ... 10. True or false? It says 12 is not in a set, is not an element. True, exactly. Very good. And also, the order of the questions in the review is shuffled. So when you do your own review, you will see different order. And also, the questions are randomly generated, and the question might be different as well. But those questions are not new. You should, at least most of them, you should have already seen them. No surprise. Universal set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Set A contains 1, 2, 4, 6. Set B contains 1, 2, 10. And the result, the question is about A intersect B, right? The common elements. A and B have 2 elements in common, 1 and 2. So we should choose A. Yeah, the intersection of AB has 2 elements, 1 and 2. 1, 2. Use a comma to separate answers as needed. Complete the truth table for the given statement by filling in the required columns. So this is about truth table. Let's see. 1, 2, 3, 4, 4 columns. Column 3 is a negation of column 1. When column 1 is T, negation is F, T, F. When the statement P is F, negation is T, F, T. Right? The third column is pretty straightforward. The last column is a disjunction. I hope you see it. It's a disjunction. It's a disjunction. And the 2 pieces in the disjunction are the 2 columns next to it. First piece Q, right here. Second piece not P, right here. And those 2 pieces together give this disjunction, right? Disjunction. So they have the idea order we want. The 2 pieces and then follow with disjunction, right? What's the sentence that we need to memorize about disjunction? There's only one case in which a disjunction is false. That is when both pieces are false. Do we have FF? Yeah, we do. FF here, so F. And that's the only case the disjunction is false. That means all other cases the disjunction is true. T, T, T. And then we're done. This one is very basic. All right? Okay, next. Oh, this is about the Euler diagram. This is what we learned today. And let me copy paste, then we have more space. We can see the whole picture. When I try to zoom in, and then we can only see small part of the picture. So let me copy paste everything here. We can see the better. So A, B, C, D, 4 diagrams. Hold on.
Due to incoming inclement weather, all TCC campuses will be closed, and classes canceled on Tuesday, February 18th. See email for more info.
This does not affect us, okay? This does not affect us. Because we are remote class. Even Wednesdays cancel, we still meet online. This is A. I hope you are not disappointed. B. This is B. And yeah, there's a lot of information in the, and this is a CD. All right, now we can see the whole thing. Someone left a message. Let's see. Sorry about missing the class last week. Oh, yeah. It's closed, but our remote class is not affected. Yeah, snow day doesn't affect the electricity, right? And now you know. Let's look at our problem. Yeah, it's okay. I have the class recorded. He or she, what is that? The following is an excerpt from a speech by a renowned cook. He or she who is without concern for quality can work with low quality means there is no one here who does not have a license in his or her pocket. I know, and I know them by name. And what he said doesn't matter because the above argument can be expressed as shown below. Yeah, this is important, okay? This is important. Premise 1, no cook is one who should work with low quality meats. That's the first statement, first premise. No cook is one, so it's quantified, right? So that gives a disjoint relationship, the first premise. Second premise, all people here are cooks. So that gives a subset relationship, right? So conclusion says, no person here is one who should work with low quality meat. Okay, I think we need 3 circles. We can also use method of elimination. If you take a glance of ABCD, all of them only involve 3 circles, right? So that means we definitely have 3 circles. And we can use this as cooks, right? This circle represents cooks, all the cooks. And this circle represents people who work with low quality meats. Material is bad. So we have the 2 circles disjoint. Second premise, all people here are cooks. So we should have a smaller circle. People here. People here are cooks. So the circle of here should fall inside the circle of cooks. And then can we draw the conclusion that people here should not work with low quality meat? So basically, want to ask, can we draw the conclusion those 2 circles disjoint? Yeah, look at ABCD, guys. What do you think? After the explanation, which one is the same with mine? Person. Person means people here, right? Did you choose D? Awesome, exactly. That's correct. Yeah. We should choose D. Yeah, D is the correct one. All right. D is the correct one. People here are cooks. All people here are cooks. So the circle of all people here fall inside the circle of cooks. If the circle of cook is disjoint with meats, then person is disjoint with meats. Does the selected Euler diagram show that the argument is valid? Yes, it is valid. Right? Very good. Question number 6. The diagram shows the relationship between two sets. A. Use the diagram to write a statement beginning with the word all, some, or no. So this is about quantified statement. To illustrate the relationship between the sets. Yeah, we encounter this in homework, right? All those questions are from your homework assignments, from the same pool. B. Determine if the statement in A true or false. If it's false, write its negation. All right. This is a quantified statement. All A are B, right? All flowers are roses. So we should choose all flowers are roses, right? Because the smaller circle is flowers, the bigger circle is roses. I know it's not true, by the way, I know it's not true, but it doesn't matter. We are just trying to translate the relationship between the two sets given by the diagram. Based on the diagram, we have all flowers. Yeah, the diagram is saying all flowers are roses. All flowers are roses. So that's first part. Part B, is the statement true? Of course not true, right? It's false. Of course not all flowers are roses. Some flowers are not roses, right? Some flowers are not roses. Do you guys remember the negation of the 4 types quantified statement? So all A are B. Its negation is some A are not B, right? So all flowers are roses. Its negation is some flowers are not roses. Yeah, that's it. Question number 7. PQR represent the following simple statements. P says I study, Q says it is time to sleep, R says the stove is hot. Write the following compound statement in its symbolic form. If I study or it is not time to sleep, comma, then the stove is hot. Okay, I see if something something, comma, then something something. So we are looking at a conditional structure, right? So I put this notation, this symbol here, conditional. And let's see the two parts in the conditional, antecedent and consequent. Antecedent is the part follow if. Where's my statement? Oh, it's right here. I study or it's not time to sleep. So the antecedent is a disjunction, right? Yeah, the antecedent is a disjunction. The antecedent is a disjunction. The antecedent follows if. I study or, so I'm gonna have this notation, disjunction. In the two pieces, I study or it is not time to sleep. I study is P. It's time to sleep is Q. Not time to sleep is not Q. Negation of Q. And the consequent is the part following then. The stove is hot. The stove is hot is R. All right, guys. Look at my entry. Do you agree? Consider the order of dominance. I do not need a parenthesis, right? And also pay attention to how do the order I enter the answer. I notice is a conditional, so I put this. You can do that on your scratch paper. Yeah, I put the arrowhead. I know it's conditional, and then I look for the antecedent and the consequent. The antecedent is a disjunction, so I put the disjunction symbol here, right? And let me know. Very good. So this is true. Yeah, I study or it is not time to sleep. Implies the stove is hot. It doesn't make any sense, but it's just you know, the logic, symbolic form. This one is about set theory. On the homework, it flags it as wrong without the parentheses on some questions. You are right. Some questions need the parentheses because let's say if the statement contains disjunctional conjunction, you have to have parentheses because they have the same level of dominance. It really depends on what the statement want to say. The reason we do not need a parentheses in previous problem is because you have not completed all parts. Okay, let me show you what's the statement earlier. The statement earlier is P or not Q implies R, right? We do not need a parentheses. If we really want to put, we do this, but we don't need it because conditional has the highest dominance. So we know it is a conditional, right? So we do not need that. We don't need this one either. Yeah, because we don't need this here because disjunction has a higher dominance than negation. Yeah, because when we do not, without the parentheses, still show the correct structure of the statement, then we don't have to have it. But some statements, the parentheses is necessary. Let's see if we can find some problem later when we go through the review, all right? And question number 8 is about set theory. We have U, universal set and set B. And what are we looking for? We need to find the sets A or B prime. Okay, how about let's do that on a note. We want to know A union B. We want to know this, right? And we have to know A union B first. Let's find A union B first. Union means OR, at least one. So we're going to include all the elements in A or B, or OR here is the inclusive OR. Let's see. 1, 2, 3 not. 3 is not in both, not either, right? In neither. So not 4, yes. 5 is not in both, either of them. So 5 is not in it. 6, yes. 7, yes. And that's it. A or B. All right, A or B contains 1, 2, 4, 6, 7. 1, 2, 4, 6, 7. And our goal is to figure out the complement of this set, right? The complement of this pink set. Now all we need to do is to cross out the elements in the pink from the universal set. We're going to cross out 1, cross out 2, cross out, let me clean this up, 4, cross out 6, cross out 7. So we have element 3 and element 5 left. 3, 5. So you're going to do those on your scratch paper. Do not try to use your brain power, try to figure it out or guess or gamble. That's not going to work. Do it step by step on your scratch paper and then put the answers in the cell. 3 and 5. 3 and 5. So like that, okay? Use comma to separate answers as needed. Next, determine whether the set is finite or infinite. This one is pretty straightforward. The key is to understand the elements in a set. This is a well-defined set, so the elements are clearly determined. And we should know what elements are in the set. This capital N represents the natural number set. The elements in this set are natural numbers that are no more than 11 million. The set contains all elements. The set contains all natural numbers no more than, less than or equal to, no more than 11 million. So what elements are in the set? We have the smallest natural number is 1, right? 1, 2, 3, 4, 5, 6, and so on and so on, all the way to 11 million. That's a lot of elements, but it is still finite because it doesn't keep going forever, right? So it's finite. Even in the zillion, trillion, zillion is still finite. Find a set A intersect empty, the empty set. We're going to know the empty set is empty. I mean, the empty set has no element, right? Since the empty set has no element, the intersection of A and the empty set is also empty. Because there's no element would belong to both. Because there's no element belong to the empty set at all. So there's no element belong to the intersection of the two sets. Number 11. The circle graph shows the most important problems for the 30,316,636 high school teenagers in a country. Without using a calculator, estimate the number of high school teenagers for whom doing well in school is the most important problem. This question requires you know percentage. All right. So the pie chart here represent all the 16 million-ish high school teenagers in the survey, right? Some of them are red, some of them are blue. Yeah, we concern the blue one. Part of the subjects they consider doing well in school is the most important. So we want to know how many students there. So doing well in school account for 11%. 11% of 16 million-ish. So we're going to multiply 11% with this huge number, okay? We use 11% to multiply the total number of high school teenagers. So we are trying to estimate 11% times that huge number. Instead, without using calculator, we would have to round it, right? Is it reasonable to round 11% to 10%? And is it also reasonable to round 16,636 down to 16 million? Right, it's 60 million-ish. Okay, think about 10% of 6 million, 16 million. 10% of 16 million, 16 million, 10% of it is 1.6 million, right? 1.6 million. Do we have a 1.6 million? Yeah, right here. See that? I believe you saw the question in your homework. Same thing, probably number a little different. Let's do this one as the last one. Obtain an estimate for the following computation by rounding the numbers such that the resulting arithmetic can easily be performed by hand or in your head. Then use a calculator to perform the computation. How reasonable is your estimate when compared to the actual answer? Okay, round the two numbers to the nearest 10. They tell you how to round. 319 can be rounded as 320, right? 320, yeah. And 579 can be rounded to 580. You have a 20 here, you have an 80 here, right? You have a 20 here, you have 80 here. 20 plus 80 make 100. So 320, 580, 300, 500, that is 800. With another 100, 900. So my estimation is 900. All right, 320, 580. Yes, 900. The actual sum, then you can use a calculator. Let's get a calculator. The actual value, 319 plus 579, 898. 898. 898. The estimation is so close, right? Very close. Very reasonable. Only two off. 2 points off. Reasonable, the estimate is a little bit higher than the actual. Reasonable, the estimate seems a little higher compared to the actual answer. And that's the one. Okay, that was question 12. Yeah, let's remember we finished question 12. Let me show you how to keep what you have worked on, and then you can continue next time you, for example, you want to stop here and eat your meal or do something else, right? Do not submit. If you submit, you have to start it over again. Do not submit. You just you can just simply close the page. Next time when you go to Pearson, it's still there. You can just pick up from where you left. All right, guys. Thank you for coming. Please spend time on the review and get a review passed as early as possible. Where are you posting the recorded lecture? Oh, that's a good question, Levy. Let me show you. This is our black course shell, right? And then we go to virtual classroom. Do you see 3 bars? That's sandwich. Click the sandwich. And do you see recordings? And those are the recordings from the past. This one's from last time. You see the date on it. For today's recording, once we finish the class, maybe take half an hour. Did I answer your question? Okay, very good. All right, Essential, I'll see you in 10 minutes. QR, I'll see you on Wednesday. Okay, bye-bye.